The last topic we're going to talk about in this class is lift. Lift is analogous to drag. It's a related process. So both of these forces, lift and drag, have to do with the interaction between the fluid and an object at the interface. Now, lift is entirely a function of pressure. There's no shear stress involved in lift. It's the pressure distribution that results around that object that causes lift. Drag was the resultant of those forces in the direction of the flow stream, whereas lift is the resultant of those forces perpendicular to that direction. In other words, upwards, normal to the flow stream. Since it's analogous, we use basically the same equation. The only difference is we have a coefficient of lift instead of a coefficient of drag. And we talked about the coefficient of drag being a function of all kinds of dimensionless numbers. Coefficient of lift is primarily associated with shape. So it's how we design that object that we use to generate lift that is the most important. And we use airfoils to generate lift. And they do that by two different mechanisms or two different properties. One is airfoils can be asymmetric, and that asymmetry can generate lift. So if you look at this wing or this airfoil, you can see it's curved, and it's that curvature that generates lift. You can also generate lift with angle of attack. So here's another airfoil that is completely symmetric, but since it's tilted into the wind, it will generate lift just because of that tilt. And then we often combine these. We can use an asymmetric wing that is angled, and that will generate even more lift. Okay, the conventional explanation, or the old explanation for lift, relied on Bernoulli. And when I learned this in high school, this is the way I was taught lift occurs. And it's in the last 10 years, we've decided that this explanation is really incorrect, and it's not a good use of Bernoulli. So I'm going to go through right now maybe how you have heard lift is generated, and it's wrong. And I want you to see if you can spot the inconsistency here in this line of reasoning. I should also say that this is a bit controversial. There's a lot of old-timers that still don't like hearing that Bernoulli doesn't explain lift, but this is the consensus now, and I think even your textbook has got this wrong. So if you read it carefully, I don't think it's quite correct in how it describes lift. So if we've got an airfoil and we've got fluid flowing past it, and if you can draw those streamlines, you can see the streamlines follow the shape of the airfoil. Let's imagine two particles or two little packets of air that are in front of the wing, and one of them is going to travel over the wing and the other one's going to travel under the wing. And let's see what happens as they get to point B. Now here's how the conventional explanation describes lift, and see if you can spot the inconsistency. Air traveling, or that particle traveling over the wing, has farther to go because of the way the wing is curved. To get to point B, the same time as the particle underneath it goes, it's got to speed up to cover that extra distance. So over the wing, you have higher velocities than under the wing. And then we can fall back to Bernoulli, because we know if you've got higher velocity, you've got lower pressure. And it's that low pressure above the wing, or rather the pressure difference between the bottom and the top of the wing, that gives us lift. Okay, so the inconsistency here is really this second point. There's really no reason that the particle going above the wing has to arrive at point B at the same time as the particle below the wing. There's nothing that requires that. In fact, when they measure this, the particle above the wing actually gets to be faster than the particle below the wing. So that statement itself is incorrect. And if you remove that statement, although the rest of this is true, you really have no explanation as to why. Why does the wind go fast? Why do the particles go faster over the wing than under the wing? So there's really no explanation of why here. I mean, it is true that you have low pressure above the wing, high pressure below. You have high velocity above the wing and low velocity below the wing. And that's all consistent with Bernoulli. But it doesn't tell you why it happens. I think it's much better to think of lift as a reaction force. So if we take this airfoil, and again we have our streamlines going around it, and we track a single particle that's traveling over the wing, or you could do it under the wing too, actually. And as you track it, you'll notice that the particle tracks the shape of the wing, and after it's passed over the wing, it's at a lower elevation than it started. And that's really all there is to it. The wing is pushing air down. Now, why does it follow the shape of the wing? Well, we learned this the first week of class. This is a product of the no-slip boundary condition. If you have a viscous fluid, and all real fluids are viscous, it will stick to a solid object that's submerged into it. So this flow stream has to follow the shape of that wing. It's a property of being a viscous fluid. And then the rest is just Newton's law. Since the airfoil is pushing air up, to every action there's an equal and opposite reaction. So since the airfoil is pushing air down, that means air is pushing the airfoil up. And I like this because it's very intuitive. The airfoil is really just a pump that's pumping air downward. And if you're doing that, then the air is pushing the plane upward. And you can feel this when you stick your hand outside the car and you tilt your hand a little bit to give it an angle of attack. You can feel the wind pushing your hand up. That is lift, and that's all there is to it. It's a very intuitive process. The other thing I don't like about Bernoulli is it implies some sort of mysterious phenomenon that accelerates air over the top of the wing, and then it's that high velocity that results in low pressure that sucks the wing up. It's really not like that at all. I mean, an airliner that's takes off by absolute brute force. If you do the calculations, a 250-ton airliner pumps 250 tons of air down per second. So it is, holding itself up by brute force. And I do want to point out that the other parts of this are true. You do get high pressure on the bottom of the airfoil, low pressure above it, and that's necessary for lift because it's that interaction at the surface that the force actually gets transmitted. And then you should also be familiar with the term downwash. If you ever got the opportunity to be under an aircraft while it's taking off or landing, you can feel this tremendous wind pushing downward. So you can directly feel that airfoil pumping the air down.